mentioned Rambler, and I heard he mentioned spam a lot of times. Well, actually, I worked there for 4 years, and I left in 2009. So that's I even don't usually mention it anymore. It was 2 years ago, but that's okay. So I'm from Moscow. If any of you want to hear something from my slides in Russian, I can repeat it in Russian, but most of them are in English. So first I'll start with talk about the sessions in web applications and one huge way of doing that. These are the permanent addresses of my channel. The first one is in English and the second is in Russian. I gave this talk in Russian 2 times, so the slides are always the same, I just translated them. I also wrote an article about the approach I'm going to present here for Dancer Advent Calendar. It's a very nice tradition in Perl community doing Advent calendars just before Christmas. So the link is in my slides. Now I'm going to show you some protocols. This is the simplest form of HTTP. I understand that this talk is less about Perl and more about HTTP. So it will apply to more wider audience. This is the simplest form of HTTP. The browser sends a GET, web server responds and closes the connection. Browser then sends the second GET, then web server responds and closes the connection. This is an example of what we call a stateless protocol, a protocol that where each transaction is independent of all the others, of the previous and of the succeeding transactions. And the other big family of protocols are stateful protocols, and this is one example of stateful protocol. It is a POP3 protocol. When a mail user agent, like Outlook or Thunderbird, connects to the mail server, it maintains the connection, and inside this connection there is a state. When mail user agent first logs in, it presents its credentials, and mail server remembers them during all the next commands. Then mail user agent gets the list of messengers, and these numbers are only valid inside these transactions because they are part of the state. This is one example of a stateful protocol. Stateful protocols are inherently less scalable, and maybe the simplicity of HTTP made it so popular nowadays. It just scales horizontally very good. Well, in 1994, Netscape invented a way to keep state inside HTTP. What they invented is called cookies. I hope you can read it. It's from a Russian supermarket. These are the simplest form of emulating state inside stateless HTTP. The server sets a cookie. It sends a small little piece of information, and the client then returns the same information within each request to the same server, and it also may include the path in URL, but the simplest form is this. So this is how HTTP with cookies work. This is a scheme of a shopping cart session in an electronic shop. The browser gets a listing of some goods. The web server responds and closes the connection. Then the client wants to buy something. It sends something with ID of the good that it wants to buy. And the web server inserts this ID inside a cookie. So all the next requests from the browser will include this cookie, and the server may recognize this card, and it will add goods to it. And when the browser wants to pay, the web server knows what to pay for from this cookie. When the payment is made, it just clears the cookie. So this is the whole transaction. And we see that the connection is broken after each request. And actually, this might even be different web servers, because all the information that connects these transactions, that links them, is inside cookie, and the cookie is stored on the client. Gradually, with the development, since 1994, with the development of web applications, the data that we want to store on the client grew. So someone invented sessions. Application web sessions are, well, they are a way to store more data using a stateless protocol. Now I will show a scheme of HTTP with sessions. Now you see that it gets more and more complicated, and I will present a simpler way in the end. So now we have three actors here: browser, web server, and a database which stores the sessions. When browser wants to buy something, web server creates a session. It stores the ID of the good inside the database, and the only thing that goes into cookies is the ID of the session. So everything goes like this. Instead of storing something into cookies, web server stores. Stores everything in the database, and the web server uses this ID to find the appropriate records in the database. Well, then the data that we want to store in sessions shrank, and sessions started to be used only as authenticators. Everyone who wrote a web application with the functions of register and login, and without using any framework, knows a function called like validate session or is session valid. Everyone writes them. This is the way that sessions are usually used nowadays. Nothing gets stored in the database except for the ID. The ID is used as a temporary, something like a temporary password. The user gets one when he logs in, and everything that he does in the interface gets stored in some other databases. The sessions are usually tables of like 2 columns or something like that. So the databases are used as secure cookies. Instead of storing passwords and cookies, we generate one-time password, which is actually a session ID, and store it in a cookie, and use the database to get real user ID. So, what are the three main features of a secure system? The first one is secrecy, the second one is integrity, and the third one is availability. These are, this is the base. And the database is used to ensure all of these features for cookies. Another simple way to create secure systems is cryptography. So the idea is to use encrypted cookies instead of the database to store the session data. Well, this is the main slide of the whole presentation, because this is the whole idea. Instead of storing the data in a database, we just encrypt it with a secret key that is stored on the server and is not shared, and send the whole data to the browser. So the secrecy is achieved using the good, strong crypto algorithm and secret key. The integrity is achieved using a checksum. We just include a checksum of the data inside an encryption function, and the availability does not change. So this is the scheme of the HTTP with encrypted cookies. There is no session database at all. This setup does not require any database, and I think that this is the main advantage of the scheme. It may be made very, very, very fast. We used it for very performance limited setups to achieve more than 2,000 requests a second. The process goes like this. When the browser posts, it logs in, the web server just encrypts this simple hash. Login equals Vasya. And this is the encrypted and serialized version of this data. It gets sent to the client. Client, since he doesn't know the key, he cannot tamper with the data, he can not see what's inside. He just returns it, the web server decrypts it, after the decryption it verifies the checksum, and this is the whole validation of the session. If the checksum verifies, then the session is correct, and we just go on. On each transaction, we decrypt the session, then we add some data to it, then we encrypt it again. Decrypt, encrypt, decrypt. When log out, then it's decrypt and clear the cookies. We have some implementations of this algorithm for popular Perl frameworks. Actually, this is the only slide that is dedicated to Perl in this whole presentation. Dense session cookie is the one that I wrote. Then Majalicious framework has this mechanism built in. We have a plugin for Catalyst and a good middleware for ESGI applications that does the same thing. You can use any of these, or you can write your own, because it's really simple. So I am going to repeat the whole scheme one more time. Sessions are not stored anywhere. Sessions are only stored inside the keys on the client, so the browsers of the sessions. On each request, the server decrypts the cookie, then he verifies it, then he encrypts it again and sends it back. Actually, decryption on modern CPUs, decryption and encryption of a cookie is much faster than querying any DB. It is usually even faster than querying Memcached or any other RAM database. verifying the checksum validates the session. So this is the whole presentation. I will take questions, but I have some time, so I will talk about some issues in this scheme. First, there's an attack vector called replay attack. The problem is that a browser can store all the previous versions of cookies. A malicious browser can send any cookie that it had ever received back to the server. So it may present the server with some previous versions of a shopping cart, previous version of anything you store in a session. And there is actually no way to fix this problem. So if your application depends on uses the session as a trusted storage, you cannot use the scheme. There is no way to force logout. You cannot invalidate a session from the server. The only way is to change the encryption key, but that will invalidate all the sessions. So if you some web applications really require a function to log out some specific user, and with this scheme, this is not possible to implement. And the third problem is the problem of session expiration. It's not really serious, because first you have an expires clause inside set cookie header, and all the browsers will honor this clause, but a malicious HTTP client may still send back a cookie that has expired, and to fight that problem, you may just store a timestamp inside the session and verify it alongside with the checksum. That's simple, but that will increase the size of the session. So that's all. I will gladly answer all your questions, but first I will answer the question that gets asked every time. People ask how much data you can store inside a cookie. And the current best practice is to store no more than 4 kilobytes of data. 4 kilobytes will work in each browser that is nowadays on the market. Most modern browsers will store even more, but 4 kilobytes is very conservative. And still 4 kilobytes is, well, it's a lot.
How does the decryption and deserialization scale when you have 4 kilobytes of data? Will the performance still be as good as?
That's a good question. Most decryption and encryption algorithms scale linearly because they work in blocks. My implementation for Dancer framework uses the AES algorithm, the current standard of the USA, and it's very fast. So I may say that probably all cryptographic algorithms in use now will be much faster than querying a database.
How much is increased the traffic when you use this authentication mechanism instead of simply a session IDs?
That depends on how much data you store in a session. If you use a session just as a one-time password, a one-time authenticator, and sessions are usually used this way, now then the size is very small. If you start to store more and more data inside sessions, then your cookies will grow, and well, yes, you will start to notice it, but it's always a good idea to serve the data that doesn't depend on cookies from different domains. You know, so if you minimize the URLs that are required to send, to return, and to accept cookies, then you can minimize the effect of growing cookies. That's it.
And one more question about performance. ICE is quite CPU intensive algorithm, so even though you can save some database queries, should it be faster than querying a memcache instead of decrypting all the time with this session? Because decrypting is a really CPU intensive task.
Actually, it's not. It is usually believed that cryptography is CPU intensive, and it's really not. Modern algorithms are really fast, and we have implementations that are optimized for each CPU. And okay, I will take this question as a request to include benchmarks in my presentation the next time I present it. So, if no more questions now, I can answer. I will be here till
5 o'clock.
Well, till 5 o'clock, so I will gladly answer any questions anytime. And I will also have my second talk later. Now, welcome Alexei.